This we call cotangent space. As I said before, I'll talk to this, okay, I'll show in detail this when we talk about the manifold. You see, the basis, look, partial Ci, this is a basis. Attention now, I is covariant because it's in the denominator, okay? Exactly like here, you see? This corresponds to this I over here. Now the component, here I have Ci and Vi. Same, analogous. Now the coordinate space, you have the vector, the basis vector, dxi. This is Ci, this is Vi. You look at here and look at here, okay? It's analogous. So I can write, okay, what is called inner product. In exterior, in this case, extrinsic geometry, okay, we talk about dot product. In intrinsic geometry, there is no dot. There is no dot, see? Because there is no scalar product, okay, dot product, okay? So you call inner product, and the symbol is like that. This, I have partial Ci d Cj is equal delta Ij. Now, you see, the left-hand side, I behaves as covariant. That's why you have I here, okay? Lower index. And J is over there. So this basis here, you see analogous to this one. You look at here as you study and you see that. So this behaves as a basis. Attention now. I can express any vector here as a linear combination of this basis here, okay? Like this one, I can express any vector as a linear combination of this. Likewise, I can express any vector as a linear combination of this over here, okay? The same linear combination of this, okay? That's clear, okay? It's a very, very, very useful when you're gonna develop in more detail the exterior algebra. So that's you see here, you go there. See now, you see here the inner product Ci Cj is Gij. Now, I behaves as a lower index in the denominator. Likewise, J, so you have Gij. Okay, and also the inner product dxi, dxi, dxj is equal Gij. See? Gij. So here we don't talk. I'm insisting, okay, and emphasize what I said. There is no vector here. There is no arrow. The arrow, like here. There's an arrow here. You see? It's a vector. There is no such word. Okay? A vector. There is no. Okay? And also, you see, you learn that AI, Aj they are not necessarily orthogonal. You remember that, okay? Likewise, if we call this vector, you see, they are not necessarily orthogonal, okay? Neither unit. There is no unit here. It's by definition. Why? Why? Because the definition of a tensor as a map, you see, this is a map, okay? This base act on this one and result and lead to a scalar. That's a definition of a tensor. Likewise, this one, okay? I have this one and this one, okay, like the same as here, okay, this act on this base and result on a scalar. That's the definition of a tensor. So you see clear that correspond a first order tensor. What we call Dixie J was called one form. DCI is called one form. When we will analyze in more detail the exterior algebra, you see that the scalar is a zero form. There is a 2 form and 3 form and so on. You see, I'll show here. You see, Dixie I, attention now, this is a tensor product. Dixie J is equal to form. See? Exactly as we did here. So do you remember the space AI, tensor product AJ, okay? They belonged to the, not as a vector V, but the vector V here. Now, so likewise this is there. So I have AI, AJ, here AI, AJ. You see, this belongs to this space here. This belongs to this space here. So I can expand in linear combination of these bases. See? So this will be a basis, a 2 form. Okay? Now, I'll talk many times later, okay, in other videos, about the exterior algebra. This is just an introduction for you to realize that we need a point on the surface. We need a point, but there is no position vector that results in a point. No vector, no. It's completely different. Okay, and this will be useful. Attention now. Okay, for physics, mechanical engineering. Okay, also when extend this to a higher dimension space, like for instance the Einstein field, Einstein equation field, we extend this to the 4 dimension. Okay? No problem. But attention now, this never we extend this to a higher dimension. Okay? This case, the extrinsic geometry only applied to 3 dimensions. This one applied to 3 dimensions, okay, in higher order dimension. See? So that's important here. So I'm talking. Attention now. I could expand this to the higher dimension, but I'm an engineer. Okay. For application, engineering application is only until the 3 dimension. Okay? Like in linear algebra, you see, when you study linear algebra, you can study for any dimension, m dimension, no problem. I'm saying my viewpoint is about the application for mechanical engineering, physics, civil engineering, okay? So the mathematician probably will not like this, okay? Because they want to extend to the n-dimensional space. So that's it. That's important. But I will insist this. For the intrinsic geometry, okay, it's important to understand that we can apply 3 and 4 dimensions because for instance, in the relativity theory, okay, you deal with 4 dimensions, okay? Not 5, 6, and so on. It's 4 dimensions. Okay? All this theory here is applicable in 3 dimensions and 4 dimensions and so on. Okay? That's it.